So as we move into this unit, it's called Oxidation Reduction Reactions on page 625 in your Merrill chemistry text. And oxidation reduction reactions are a special kind of chemical reaction. It's a special type of reaction, and we've, of course, talked about categories of reactions in Physical Science 20, combustion, synthesis, decomposition, single and double replacements, and acid-base, that sort of thing. So we talked about that last year, and those are types of chemical reactions, but a subset of chemical reactions that we need to talk about today are called oxidation reduction reactions. And these are important because the difference between oxidation reduction and just a regular chemical reaction is the transfer of electrons. Now, we've always talked about chemical reactions as a rearranging of atoms, right? Which is absolutely true. But when those atoms rearrange, sometimes they also transfer electrons out to themselves or away so that they become ions, or maybe they drop their charge to rearrange. And so at this level, what we're going to talk about is how to recognize an oxidation reduction reaction, often called a redox reaction, just for short, and how to balance a redox reaction, which involves balancing all of the electrons that are transferred as well. So there's just a kind of a deeper level of understanding and working with these reactions. So in your notes, we're going to go through this rather quickly here, but I'm just going to highlight a few things. Feel free to make notes in your margin or to highlight or whatever. Those notes that you have are yours. But so redox reactions, okay, is a short form here. The type of chemical reaction, as I mentioned, that involves a transfer of electrons between two species. Now, the reason why I say species and not between two atoms or between two ions or whatever is simply because we are talking about either atoms or ions. And so when I say species, I just mean a certain substance. Could be an atom, could be an ion. Okay, could be a diatomic molecule, whatever. An oxidation reduction reaction is any chemical reaction in which the oxidation number of a molecule, so we're going to have to go over what those are, oxidation numbers, of a molecule, atom, or ion changes by gaining or losing an electron, an E with a little negative exponent, abbreviation for electron. Right? Oxidation number is the charge of a monatomic ion or the apparent charge of an element in a compound. So that's just the sort of general definition of what an oxidation number is, and we're going to practice, take a look at how to identify oxidation reactions. So these type of reactions occur every day, and they are vital to some of the most basic functions of life. Some examples include photosynthesis, respiration, okay, breathing in and out and the intake of oxygen, combustion, and corrosion, or we talk about rusting as well, corrosion. So to understand these types of reactions, you must first understand oxidation numbers, or also called oxidation states. Okay? So the oxidation state is also referring to what's the oxidation number of this element in this case. So Chemistry 20 or Physical Science 20 review for oxidation numbers. Okay. So oxidation numbers, as we mentioned up here, it's first of all, it's the apparent charge, the charge of a monatomic ion. So if you look down here, you see sodium 1 plus or plus 1. If you see that in a chemical reaction, then the oxidation number for sodium is plus 1. Or chlorine negative 1. So if you have an ion, a monatomic ion with a charge, that charge is the oxidation number. That's the easiest sort of thing to recognize. Okay? But let's go through these rules here. The first one states that if you have a lone element or an individual atom, okay, in a chemical reaction, then the oxidation number, or the oxidation state, OS is oxidation state, is 0. So if you have iron, solid iron reacting with oxygen, both of these would have an oxidation number of 0. So if it does not have a charge, if it's a neutral atom by itself, it's 0. And you can think about, what's the charge? Well, there's no charge, it's 0. Okay? Number 2 says the total oxidation state of all atoms in a neutral species has to add up to 0. So the total oxidation state in a neutral species is 0. And here's where they say in an ion it's equal to the ion charge. Alright, so sodium chloride, alright, you know that sodium and chlorine must add up to 0, and there will be rules for the very first column with sodium is in, and also the halogens. Okay, these guys are always +1, these guys are always -1. But if you're looking at this as a whole, you know that because it's a neutral compound, all of the oxidation states have to add up to 0. That's what that second rule says. Okay, rule number 3, group 1 metals, that's what I just mentioned, the sodium, lithium, sodium, potassium, rubidium, cesium, francium, they have +1, so that's group 1 or column 1. Group 2 is always +2, so beryllium, magnesium, calcium, strontium, barium, radium, those are always +2. Number 4 says the oxidation state of fluorine is always -1 when in compounds, okay, and in almost all cases that I can think of, chlorine, bromine, and iodine, the rest of the halogens are all also -1, okay, in almost all. So it says fluorine, okay, but you can also add, if you want, and I'll just add that, okay. So chlorine, iodine, bromine, also in most cases. So it's really just the halogens. You'd be safe to say the halogens are -1 in 99% of the compounds they're in, but fluorine is always. All right, number 5, it says that hydrogen generally has an oxidation state of +1, and that's again 98% of the time +1. Hydrogen is +1. There are some cases, like in hydrogen peroxide. Wait, is that right? Peroxide, lithium, or lithium hydride, I should say, where sometimes it's -1. And on your periodic table that I gave you, you see that hydrogen is a +1, and also it's on the other side of the table where hydrogen is a -1 sometimes too. So that doesn't happen very often, but when it's in the formula listed second, like I mentioned, lithium hydride, this is a +1 always, this then is a -1. Okay? But most of the time it's not like that. That's very uncommon. Number 6, oxygen generally has, oh yeah, this is the one I was thinking of. Oxygen is -2, except in things like hydrogen peroxide. It's not. H2O2 would be each a -1, because these would be each a +1. So hydrogen, that's one of the exceptions, but that doesn't happen very often either. Number 7, in binary metal compounds, group 17 elements have an oxidation state of -1, so that's the rest of these as well. Okay, so we said most of them in binary. In group 16, -2, 15, -3. So group 17, -1, group 16, -2, and group 15, -3. So on your periodic table over there, it's just working backwards. So halogens, and then oxygen, sulfur, selenium, tellurium, and then nitrogen, phosphorus, arsenic, antimony, as you work backwards, okay? -1, -2, -3, whichever. All right, the sum of the oxidation states is equal to 0 for neutral compounds, but this one we haven't mentioned yet. It's the sum of the oxidation states is equal to the charge for a polyatomic ion species. So if you have something like NO3 minus, okay, all of the oxidation states for all of these elements here have to equal -1. Okay, and that's where you get a little bit, you can get some different oxidation states for things like nitrogen. Oxygen, it's going to be -2, so that's going to be a -6 for the oxygen, and because it's a -1, nitrogen is going to be a +5, and you wouldn't guess that, right? So that's where it gets a bit tricky. You sometimes have to sort of deduce what this charge is. You can't just look at the table all the time. But suffice it to say that all of the oxidation states have to add up to the charge. Okay? Questions so far on the rules? Are those ringing a bell, or have we talked about those? I can't remember. I think we did talk about those in Physical Science 20, but because it's changed a little bit, I don't think we spent too much time on that, to tell you the truth. Probably not. That's probably the first time we've seen it. Okay, let's just get some practice here. Let's get some practice. determine oxidation states here. Iron, what's the oxidation state in iron? Anybody want to guess? I think I heard it. 0? Yes, because it's a lone element. It's got no charge. It's 0. What about oxygen? Yes, it's also a lone element. Doesn't matter that it's diatomic. It's all by itself. There's no charge. So it's 0. All right. Now, this, we have to go back to how we write formulas, right? The reason why this is Fe2O3 is because of the charges of iron and oxygen, right? Now, oxygen would have a charge of what? -2, right? So 98% of the time it's -2. That is true. So what is the charge on the iron here? Now think about what the ion of iron would be charged here. Okay, so this is a 3 times -2 is a -6 on this half, and this has to be a +6 because it's a 0 charge, and there's 2 of them, so each are +3. Okay, does that make sense? So when we formed this compound, right? This is a +3 joining with a -2, and so we write the formula Fe2O3. So yeah, so these are the oxidation states right here: 0, 0. Iron, you just say iron carries a +3 oxidation state, and oxygen carries a -2. A -2 oxidation state. Okay, that's pretty basic, right? You would have guessed that, I think, before we even talked about this lesson, right? That's what you would have guessed. So this one, oxidation state is 2+, because it's an ion, and it has a charge. All right, let's do C. Silver, 0. It's all by itself, no charge. Okay, now H2S. All right, so H is almost always what? +1. Okay, and there's 2 H's with 1 S, and even on the chart there you see that S is what? What oxidation state or oxidation number does it have? -2, yeah. Does that make sense with this compound? Yeah, it does. 2 positive ones with balance with 1 -2. Okay, so what's happening over here then? It looks like silver is now in a compound with sulfur. So what are the oxidation states here? Silver and sulfur. And if you look on your periodic table there too, you get some indication of what the ion charges would be. So what's silver? Well, what's sulfur? Has sulfur changed oxidation state, do you think? Okay, what would the charges of the ions be? Don't complicate it too much. The charges of the ions would be, what on your periodic table, what does silver has a +1, right? Does it make sense that this is a +1 and this is a -2 like you would expect? Yes. So in binary ionic compounds, you really are just assessing the charge of the ions that form those compounds. So again, if it's binary, just 2 elements, it's ionic, just figure out the charges, okay? That's all you gotta do. And H2 again is 0. Okay. So when we talk about redox reactions, I want you to look carefully at this because this is a redox reaction. Why? Because the oxidation states for the elements change from before the reaction to after the reaction, or from reactant side to product side. Silver is 0 over here. Silver is a +1 here. Do you see that? So we have the exact same element, but it has lost an electron. Okay, so if you think about it, if you were a silver, you're a silver atom here, and you're all by yourself. Okay, you've got 47 protons and 47 electrons. You're neutral. You're just an atom hanging out. While sulfur comes along, and you decide you want to bond with sulfur, so you're going to give up an electron because because sulfur likes to take electrons. So there's 2 of you guys are going to give your electrons to sulfur, and now you're still a silver, but you've got 1 less electron, right? You've sort of given that up to bond, in a sense. So that's a change. Has anything else changed? Yeah, the H has changed. Okay, so the hydrogen had an oxidation state of +1. Now hydrogen has an oxidation state of 0. Okay. And notice that we've lost an electron here. Silver has lost an electron, and hydrogen has gained an electron. So the electrons are accounted for here, right? Something gives it up, something takes it on. And so this is a redox reaction, a reduction/oxidation reaction. So these are the kind of things that we're looking for, and I'll explain what reduction means and oxidation means here. And yes, you've correctly noted that A is also a redox because iron has changed and oxygen has changed. Okay, example 2, determine the oxidation state of the bold element in each of the following. So sometimes we can't just look at the periodic table and guess what the charge would be because it's a little more complicated than that. What we have to do in this case, so for letter A, we have to look at phosphorus and find out what charge that is. We know, going back to some of the rules, okay, we know that sodium is always a +1. And we know that there's 3 of them in this compound. We don't know what phosphorus is, but we also know that in 98% of the cases, and we can assume, whenever it's not a hydrogen peroxide or something like that, that oxygen is -2. So what I'm doing is I'm just kind of writing out sort of what I'm doing in my head here. And this has to be equal to 0, the apparent charge here, right? It's a neutral compound. So what do I have? I have 3, and I'm going to have to plus or add something to -6. So 3 plus what plus -6 gives me 0. The oxidation state for phosphorus is 3, or 3 plus. Does that make sense? 3 plus 3 is 6, minus 6 is 0. All right, take a moment and you do B. Same phosphorus, but it's in a different compound. It's in a polyatomic ion here, so you figure out what P is. Go ahead and do that. Okay, so you can look up on the board when you're done there, and see if you agree with this work here, or if there's any mistakes, you think? Anybody get +6 for an oxidation state? Yeah. Okay, so hydrogen is +1 times 2. Okay. Okay, thank you. Thank you. What does this add up to right here? 2 and 6 is 8. Minus 8 is actually 0. So what does it have to add up to? It has to add up to -1. So what should this be? Okay. So up here in this one, right, we have to add -0. So that's what we did. 3 plus 3 minus 6 is 0. But this one, see the charge there is -1? All right? So this is not the charge. What should it be? 2 plus what minus 8 is -1? Got 5. So this should be 5. Does everyone see that now? Yeah? Did anyone have 5 there before I... Yeah? Phoebe? Okay. Alright. Good. So, and the solutions are here, and let's see. Explanation of the X. So it's on next page. So +5. Alright. Okay, let's move on. Oxidation reduction reactions are comprised of 2 parts. A reduction half. Okay, this is a really important part here where reduction and oxidation are explained here. So reduction half and an oxidation half. That's why it's called oxidation dash or slash reduction. They always occur together. So as I mentioned before, remember when an electron is given up, it's also accepted by something else that's involved in that reaction. So they always work together. The reduced half gains electrons. Now this is going to seem at the beginning a little bit backwards, okay? The reduced half gains electrons. The oxidized half loses electrons, okay? So you can think about this. if a species is reduced, or if part of this reaction is reduced, by gaining electrons, you can also think of it that it gets more negative, or that it loses charge. So literally that number drops. If it's +3, it goes down to 0, or if it's 0, it goes down to -2, or something like that. Okay? That's one way you can remember that, because it does seem a bit backwards. There are also some memory mnemonics, which we'll get to here in a minute. The oxidized half loses electrons. Okay? So there's simple ways to remember this. One of them is remember this little mnemonic, oil rig. Okay, oil rig, OIL. Okay, oxidation is loss of electrons. Reduction is gain in electrons. Okay, that's an easy one to remember. Oil rig. The one that I learned when I was your age in school was Leo the lion goes grr. That's the one that I always think of when I try and remember this stuff. Lose electrons, oxidized. Gain electrons, reduction. So either one, whichever one you gravitate to. But you'll have to know that really quickly, so you have to memorize that somehow as you do these questions. Okay? Now, let's see, there's no net charge in the number of electrons in a redox reaction. So in a redox reaction, there is no net change in the number of electrons. I guess it's charge. There's no net change in the number of electrons. So as I mentioned earlier, when we're balancing redox reactions, we not only have to take into account the number of atoms, but we also have to look at how many electrons are involved. And so it's a little bit trickier to balance a redox reaction with respect to electrons as well, but that's where we're going with this information. So those given off in the oxidation half are taken up by something else in the reduction half. Okay? And again, just once again to reiterate, when a species gains electrons, it's reduced. When it loses electrons, it's oxidized. The two species that exchange electrons, okay, and it's going to be either an atom or an ion that is going to give up electrons or take electrons, and they have special names. So the ion or a molecule that accepts electrons is called the oxidizing agent. The better way, I think the best way to think about it, to remember it, is the one that is reduced. So the species that is reduced does the oxidizing, okay, to the other one. It causes the other thing to be oxidized. So whatever is reduced is the oxidizing agent. And conversely, whatever is oxidized is the reducing agent. Okay? So the reducing agent is the one that gets oxidized. So there's a couple things to remember. I know this is your first time hearing this, so it's going to take some time to sink in. But when there's a loss in electrons, that is oxidation. When there's a gain in electrons, that's reduction. If something is being reduced itself, it is the oxidizing agent, okay, because it's causing something else to be oxidized. If something is being oxidized, it's the reducing agent because it's causing something else to be reduced. Okay, so you will with time get that straight in your head, but that's just something you got to remember. Okay, so in this example, we're going to determine, and don't look at the solutions just yet here on your sheet if you have those in front of you. But in example 3, determine which element is oxidized and which element is reduced. Okay, so we have to, first of all, assess oxidation states to everything, and then figure out which one is gaining electrons, which one is losing. So this can go rather quickly. This is 0, H is +1, zinc is +2, and H2, this molecule, is 0. All right? So you do that real quickly. Now, zinc, what's happening to zinc? It is gaining electrons or losing electrons. Okay, someone said gaining, someone said losing. Now the charge is going down, so are we gaining electrons? Remember, gaining electrons is getting more negative. Losing electrons is getting more positive. So zinc, okay, is losing electrons. So what is it? Leo. it's being oxidized. Is that right? Get that? Losing electrons. Now hydrogen is, it's a +1, and now it's becoming more negative, isn't it? So it's gaining electrons. So hydrogen is gaining electrons, so it is reduced. Okay? So we look down here. A, zinc is oxidized, and the hydrogen ion is reduced. So whatever it is here that is actually gaining the electrons or losing, you want to write that in. So it's actually, here it's the element zinc, here it's the ion, so whatever. Okay? Does that make sense? Okay? Alright, so B, well, aluminum. Let's just look at aluminum first. Aluminum is 0, and it's going to 3+. So is it gaining electrons or losing electrons? It's losing electrons, so that is oxidized. Right? Leo, losing electrons, oxidized. Or oil rig, oxidation is lost. I don't like oil rigs so much. Anyways, Cu2+. Okay, so we've got 2+ and 0. So this is gaining electrons to become more negative. So Cu2+ is reduced. Alright, and I'll give you guys a chance. Why don't you guys do C if you haven't looked at the answers already. Just do C, and we'll see where that goes. When I first looked at it too, I just assumed it was, but once you actually get into it, you know, it's not a bit of a tricky one. Okay, questions there? Alright. Okay, here's just some more notes for you, just explaining oxidation agents and oxidizing agents, reducing agents. I won't read that. You can read that later if you want. Here's another example, the thermite reaction. You guys have heard about the thermite reaction? You may have watched a video on that. It's a very violent reaction generating a lot of heat, and it melts metal. It's a way of, fusing things underwater or just in a really short amount of time, used on railway tracks to fuse railway tracks and fix things like that. Anyways, it's a very strong redox reaction. All right. Well, let's see. Here's just some more practice here. Yeah, 0 to 2, 1 to 0. Okay, you don't need to do that one again. Just another example. All right, so that's going to be the lesson then today on oxidation reduction. Went through these notes here. How to recognize redox reaction, how to identify oxidation states, what is the oxidizing agent, the reducing agent, and so on. So that's that.